All right, I'm Ben Lamm. Today we're going to be giving a talk on Intro to Blockchain Technology. Before I start, I just want to like a caveat to begin with. I'm not going to be talking about cryptocurrency. I'm not going to be talking about investing or finances or anything like that. Yeah, so if that's what you came for, sorry. Really, the talk today is just going to be it's going to be an explanation of the fundamental concepts underlying blockchain. So everyone can walk out of here understanding exactly how blockchain works in whatever application you choose to use you choose to use it. With that said, I'm going to be talking about Bitcoin, simply because Bitcoin was the first real application of blockchain, and it's just a good application of blockchain technology to use to teach blockchain. Alrighty. Okay, so before, just some background and history on Bitcoin. So on August 18th in 2008, the domain bitcoin.org was registered. In November 2008, a link to a paper authored by somebody called Satoshi Nakamoto. Nobody really knows who that is. The paper was called Bitcoin, a peer-to-peer electronic cash system. It was posted on a cryptography mailing list, and basically it just said it was talking about someone who was working on an electronic cash system that's fully peer-to-peer with no trusted third party. And that was that until January 2009, when Nakamoto actually released the Bitcoin software. And on January 3rd, 2009, the Bitcoin Genesis block was created. And that went until like 2010, when Nakamoto decided to take a step back. He handed over the keys and control of the Bitcoin core code to someone named Gavin Andreessen. And the Bitcoin the Bitcoin code is open source. It's publicly available on GitHub. So the reason why I gave this background is many people say, like, we don't know who wrote Bitcoin, and we don't know, it's software, we don't know what's inside. So the fact that we don't know who actually wrote it is really irrelevant. It's all open source. Everyone can see exactly what's happening in there. All right. Okay, so in order to understand Bitcoin blockchain technology, there's four fundamental concepts that we have to understand, or really to understand blockchain technology as it's being used today in a useful manner. There's four fundamental concepts that we have to understand. Number one is hashing. The second one is blockchain, and we'll see when we get there how blockchain is really just a subset. Number three is a decentralized peer-to-peer network, and number four are digital signatures. So those are the four pieces that we have to understand in order to understand what the big deal is about blockchain, and we'll go through each of these. Alrighty, the first one is hash functions. So what is a hash function? So a hash function is a mathematical equation. So it takes an input and turns it into a fixed size output. Think like a Reader's Digest. It takes big stories and like crumbles them down into smaller stories. And hashing has many uses in computer science, specifically for cryptography. So we have something called cryptographic hash functions. And these are mathematical functions that can take variable-sized strings or data and compress it into a fixed size. Like we have hashing algorithms like SHA-256 that takes a block of data of any size and compresses it into a block of data of 256 bytes. A few characteristics of cryptographic hash functions are, number one, they have to be deterministic. That means the output will always be the same for any given input. So if you take, let's say the book Moby Dick, and you pass it through SHA-256 hashing algorithm 1,000 times, every single time you're going to come out with exactly the same output or digest or hash. The second, another property of a cryptographic hash function is that they're collision-free, meaning that if you take two different inputs, you will always get different outputs. And in order to find two different inputs that have the same output would take an astronomical amount of time. It's feasibly impossible to find two different inputs that have the same output. So if you have a certain output, right? If you have an output or a digest or a hash, and it matches a certain input, you are, for all intents and purposes, guaranteed that the hash that you have came from that input. All right. Another one is it's not non-invertible. So once you have a hash, which is just a fixed size string, there's no way to go back to what generated that hash to begin with. So if you take the book Moby Dick and you put it through SHA 256 and you come out with a digest, if you just give someone that 256 character string, there's no way in the world for them to figure out that for them to go back to know that this hash came from the book Moby Dick. They can take the book Moby Dick and hash it and then see that the hashes match, but there's no way to go back. Another property is that hashes should be relatively easy to calculate. They should be relatively easy to calculate the hash of a book or any piece of data, but like we said before, non-invertible, but not the other way around. And then another very important piece is that even the smallest change, any change of a single character should change the output drastically. So if you have a book like Moby Dick, right, which has thousands of characters, and you put it through a hash function, you'll get a certain output. If you change just one letter in that book, the hash function will the second hash function will look nothing at all like the original hash function. So whereas with a lot of older ciphers, like the oldest cipher many of us know, like the Caesar cipher, where there's a one-to-one relationship between each letter in the output and the input. So if you change one letter in the input, it only changes one letter in the output. With modern ciphers, with hashing, changing one letter, one character in the input should change about 50% of the output. And hash functions are used not just for cryptography, they're used for a lot of things like hash tables, indexing, databases. Anytime we need to take some big piece of data and represent it with a fixed size, smaller piece of data, we pass it through a hash. Okay, so that's hashing. That's step one. Taking a big piece of data and turning it into a fixed size, smaller piece of data that smaller piece of data absolutely has to have come from that original piece of data, and there's no other way to have come up with that result. All right. So now another application for hash functions. So like we said, right? They're collision free, right? So that's one of the properties of hash functions. Right. So there's no way to determine ahead of time. As another property is there's no way to determine ahead of time what the hash output will be of any given input. So if you have any given input, it's impossible to figure out, to even determine in any way, shape, or form what the output will be. Okay. So if you want to get if you want an output, let's say that starts with a 1, there's no way to know ahead of time what input you'll need to have a hash output that starts with 1. You're just going to have to try a bunch of different inputs until you find one that starts with a 1. So in 1997, there was a fellow named Adam Back who came up. Email was still relatively new, and they had a problem with spammers. People were sending out millions of emails a minute, and they wanted some way to stop those spammers. So this guy Adam Back proposed a solution. He said, whenever you write an email, what we should do is take that email and find a nonce, which is just a random string of numbers, to add to that email, so that when you pass the entire email with the nonce through a hash function, it will come out with, let's say, the first 3 characters will be 0. Okay. Now there's no way to know ahead of time what that nonce should be, right? If you just pass the email as you wrote it through the hash function, it can come out to anything. So you would have to add numbers, start from 1. So write your email, add the number 1 and hash it. Add the number 2 and then hash it. And basically increment the numbers until you find a hash that starts with 3 zeros. So for a computer, it is trivial, but it'll take 2 or 3 seconds to go through, let's say, 10,000 hashes until it finds a nonce to add to the email to give an output hash that starts with 3 zeros. So for someone who's sending, and I'll demonstrate this in a second. So for someone who's just sending a random email, it'll take an extra 2 or 3 or 5 seconds to send that email. That's not a big deal. But for a spammer who's sending out 1 million emails per minute, they don't have that 5 seconds per email to find a nonce. And that was called hash cache. And I wrote just a small Python script here. And okay, so I called it find the nonce. And basically what it does is you give it a message or a string, and then you tell it how many zeros you want at the beginning of the output hash. So let's say I want 1 0, and I want to find a nonce for the string hello world. Okay, so what this is going to do is it's going to take the string hello world and tack on a number right after that string and pass it through a hash function. And it's going to look for an output with a 0. So it's going to tack on a 0 and then pass it through a hash function and check if there's a 0 at the beginning of the output. If there is none, it's going to increment the number and again and again and again until it finds an output hash that starts with 1 0. So let's run this. So again, we're looking for 1 0 for the string hello world. And we see the output says searching for a hash with an output that begins with 1 0. It should take about 16 tries. The reason it takes 16 tries is so this is the output hash. Right here, this is the output hash. This is a hexadecimal number, right? So it can go from 0 to F. So basically every time you pass a string through a hash function, like I said, there's no way to know what the output hash is going to be. So it can be anything from 0 to F. So it can be one of 16 characters. So if I specifically want a hash that has a specific 0 at the beginning of it, I could have to try statistically up to 16 times till I get the one character that I want. If I want the two first characters to be something, let's say I want the two first characters to be 0 and 0, so that's 16 times 16. So it's 256 times that statistically up to 256 times that I have to try different combinations until I find the hash that I want. So that was with 1. Let's do 1 with 3 zeros. So we also see this one took 0.14 seconds, and the output hash was 09B. So that one started with 1 0. So let's with 3 zeros. So here we have the output hash is 007, and it found this nonce 1994. And if we take Hello World 1994, and this is a SHA-256 calculator, and we see there that the hash is 00765, and that's what we got over here. So we want. And we see that it said it would have to try up to 4,096 times because that's 16 times 16 times 16. Let's try 5. There we go. So looking for a hash that starts with 5 zeros, it may have to try up to just over 1 million times. So that's 16 times 16 5 times, 16 to the 5th. And the output is hello world, and it tacked on this 139,526. And if we take this here, we see that we got those leading zeros. So this was a mechanism that this guy Adam Back came up with to say, hey, listen, for regular people who are sending emails, it's not a big deal. But for spammers, this is a big deal. Okay, so that's an important piece. Anyone have any questions on that? Cool. What's that? Is this actually being used? No, it was never implemented. Okay, so that's hashing. How would you remove? Well, I mean, I guess the email protocol would remove the nonce. It would know. Yeah, I mean, it would have a nonce field. Alrighty. So now, when we're talking about finding a nonce that gives an output with a couple leading zeros, so it's not really just arbitrarily a couple leading zeros. What we're actually looking for is a number less than a certain target. And so this chart is going to explain it. So let's say we have our message hello there, and we have a nonce of 0. So if we take the output hash, right? Let's say we take this output hash. Yeah. All right, and that is actually a hexadecimal number representative. So 000765 is actually 1893. Okay, so all these long hashes are actually they're just numbers. So they're represented here in hexadecimal, but you can think of them in decimal also. So the idea is that we're looking for a nonce that when concatenated with a message will give us a hash that's less than a certain target number. So in this example, our target number is 100,000. So if you take hello there and you add a 0 to it, the output hash, this is all just made up, the output hash would be the hex of it, that would be the decimal, and that's 9 million, it's not less than 100,000. Same for the 1, that gives us 11 million. If you tack on a 2, the output hash is, again, 1 million. If you tack on a 3, that gives us 00F4A1, and yep. There, it's 62,625. So this hash with the leading zeros is really in decimal, it's just a lower number. So the idea for this hash cache was find a hash that is lower than a certain number. In this case, it would be 100,000. But obviously, if you want even more zeros, you can be a lower number or a higher number depending on your scheme. Okay, that's the idea behind hash cache. Any questions on that?
Hash cache is this Adam guy.
Adam Back, yeah.
So meaning he didn't just say put zeros, meaning he said do this.
He said do this, yeah. And with hashing it, so it's represented with zeros. Okay. Okay, so that's hashing. Next one is blockchain. Okay, so blockchain by itself is actually really simple. We'll see soon. Blockchain is actually a really old concept. It's introduced in the early 90s. Okay, so now that we understand hashing, we can understand blockchain by itself. So what a blockchain is a chain of blocks. Each one of these, and I'll explain this in a second, is a block. And you can see there's 3 blocks here, and they're all chained together. Now, what does that mean? So this block right here is made up of 3 pieces of information. It's made up of a block number. So this is block 4. So let's say there's a couple blocks before it. It's made up of some data. So just put the string, I like chocolate. And it's made up of the hash of the previous block. Now, if you take these 3 pieces of information and you hash these 3 pieces of information, you'll come up with a hash for the current block. Okay? And this represents one block. So it's some data with part of the data is the hash of the previous block. Take all that data and hash it, and that becomes a hash of the current block. Then when you tack on another block, when you chain on another block, again, you increment the block number, put in whatever data you want, you put in the previous hash. This previous hash is that hash over here. And you hash this, and that comes out with the hash of the current block, right? And do the same thing here. So in essence, what you're doing here, so this block over here is relying on the fact that this block and all the blocks above it are exactly the way they are. Because if a single character in this data changes, right? If I take off that E, this hash will completely change, like we explained before, right? So this hash will look completely different.
Hash underneath.
This This hash over here will be completely different. Thank you. Because this hash is completely different, this just reflects that. So this will change, and then this will change. So when I have these blocks that are chained like this, if anything in one of the previous blocks changes, you'll know immediately that something is off because each block is relying on the block before it. Okay? So basically, it's a way of storing immutable records. So I want to keep a record of this information, then I want to keep a record of this information, and I want to keep a record on this information, and each one basically is like is verifying or securing the block before it. All right. So just a demo. So blockchain is a continuously growing list of records which are linked and secured using hashing. So each block is fundamentally, this is what I was trying to say before, is linked to the block before it like a chain. Okay, so let's say we have this block. Let's call it block 15. It's got a previous hash. Blockchains usually have a timestamp in it for whenever this block was created and some data. So over here, before it was just a simple string. Here we're actually going to start saving transactions. So the data here is Abe sent Bob $100. So you can see over here, this is what's actually being hashed. So 15 is the block number, previous hash, that's that. Then we got the date, then we have the message, and we take all this information, and we hash it, and we come up with the hash of the current block. Then we got block 16. So the previous hash 75186D refers back to that hash. And again, we take all this information, We hash it, and we come up with another hash. Same thing with 17. And again, each block is fundamentally linked to the block before. If anything in one of these previous blocks changes, that'll change everything else in all the blocks ahead of it, or the blocks that come after it.
How's the first block?
What's that?
How's the first block the hash is random?
The first, yeah, that is a very complicated subject. It actually is a big problem. How to create that first block. Sorry?
Why would you need that?
What?
Why would you need the first block to have a previous hash?
Well, what are you going to put in?
Hash.
Well, the protocol says in each block, every time you create a block, look at the previous hash. So you need to hard code an exception into the protocol. Right. So when the guy started Litecoin, I forgot his name. When he started Litecoin, he actually had to do a lot of research to figure out how to create that initial block. I heard a talk from him about that.
So what happens if, so let's say, the first one, the hash, somebody decides to go and change it to Bob
Here,
sent Abe.
I'm getting that right now. Okay, altering a blockchain. Okay, so this is a blockchain I just showed before. Okay, Abe sent Bob $100. Bob sent Charlie and Derek. Charlie sent to Abe. Aaron sent to Dave. All right, so we see here. So over here, initially it said Bob sent Charlie $75. Now Bob wants to go back in time and say, hey, no, I only sent him $50. So he goes and he changes this to $50. So that changes that to $50. It changes that hash. Right? So it changes this. But this block over here was relying on this. Now this previous hash doesn't match this. And the whole thing blows up. So anyone who has this block already, when Bob goes and changes this block, will say, whoa, something's off here because this block, it doesn't make sense that this block continues on from this block. Something must have changed here.
So somebody does need a copy of that third one at the end of the day.
What's that?
Somebody has to have a copy of the third one to make
Yes,
sure.
yes, exactly. Yeah.
So we're assuming they have the third one, not the second one?
We're
Otherwise,
assuming.
you can just say that they don't have the second one. Because otherwise you can just say it doesn't say anything.
Well, no, because if several people have a copy of the entire chain and somebody goes and changes one digit in one of the previous blocks and tries to convince everyone else that this change, that change will never get into the system because everyone will know right away that doesn't make sense.
That's only assuming that a later block was created.
Yes, yeah, of course. So again, so we see over here, so altering a blockchain, if you change one of the fields here, that'll invalidate this block, and that'll cascade and waterfall and invalidate all the blocks after that.
How's the last one validated? How's the last block validated?
This one over here.
Whatever the latest block is.
So
It's always
assume we have this entire blockchain and take away all the x's. So it's a valid blockchain of blocks, and many people have this block. Now somebody goes and changes this block over here, and tries to tell everyone else, hey, yo, you guys have the wrong block. So everyone else can say, like, no, we don't, because that doesn't work with any of this stuff. Like, from the fact that this block was created means that this was a valid block. The fact that this was created means that this was a valid block, so on and so forth.
the last block itself is vulnerable.
This one?
There's nothing validating the last block.
If you change the last block before a later one was created.
Yeah. Oh, you're saying the last block? If you change the last block, then yeah. There's nothing validating it. Yeah, you can change the last block. We'll see later, but yeah, there's nothing validating it. What's that? Because if right, so this is the first block, and it goes like this. If each block relies on the fact that the hash of a previous block is something. If you change one field in this block, it'll change the hash of this. But this was relying on the previous hash. So now this hash will change because this is pointing at that previous hash, and this hash will change because this is pointing at that previous hash.
Well, if it changes, how will everybody know that it changed to something that's not valid? How will they know that it's not?
That's the next step. Peer-to-peer networks. Okay, so we got two technologies so far. We got hashing and we got blockchain. So, like you can see, blockchain. This is blockchain. Like if you understand this, you understand blockchain. Like if that's all you came for, blockchain right here. Okay, but there's a lot of questions.
So all we have here is just the idea that somebody knows what that there's an alert that something changed. That's all we have.
Yeah, it's basically creating immutable records that are preserved by hashes of the future records that are tacked onto it.
I understand, but there's nothing you can do about it necessarily.
At this point, yeah, okay. There's nothing to do. If once additional blocks are added onto it, again, if you change anything back in the blockchain, you'll have to change all the blocks that came after it. Okay, so that hashing blockchain. The third of the fourth is distributed peer-to-peer network. And basically, what this means is we have our blockchain, right? So we have a blockchain that's recording. Let's say we can record any stream. Let's say it's recording transactions. Now let's say there's a bunch of friends who get together and they say, let's create this cryptocurrency where we're just recording transactions, and everybody, let's create this peer-to-peer network, and everybody will keep an entire copy of the blockchain on their own computer. Now, whenever somebody, and so Abe's blockchain, the software that's running his blockchain is connected to Bob's copy. It's connected to Charlie's copy. It's connected to Derek's copy. So anytime Abe wants to say that there's add on a block or add on a transaction, he'll send his information to Bob and to Charlie and to Derek. And Derek's connected to Evan and to Mike. He'll send it to Evan and to Mike. So basically, every time a change is made on a blockchain in somebody's computer, it'll very quickly get dispersed to everyone else in the network. Okay, that's how like BitTorrent works, and lots of other protocols that work. Any other protocol that works peer-to-peer works something like this, where you have a copy of something and you're just talking to a bunch of other people and synchronizing all your information. Any questions on that?
So this information as a currency is only applicable to the people in the network?
Yes, yeah. It's only applicable to people in the network. The nice thing about this is that there's no one in charge. There's no one like, if Derek decides to drop off, that's fine, because everyone he's connected to is connected to other people as well. If somebody wants to jump in, let's say Abe has a friend, Abe tells his friend, yo, come join our network, he could just give him the IP addresses of Bob and Derek, and then Bob and Derek can give that friend some other IP addresses, and you can quickly connect to this peer-to-peer network. So
That's viable if the currency doesn't apply outside the network.
Well, it's just for friends. I mean, and this application is just for the people who are involved in it.
Or it's just feel like, what might give you a hot dog, you pay him for the network.
Yeah, called fake internet points, Reddit karma. Okay. This is the idea of a peer-to-peer network. Okay, so this is number 3. So we got hashing. With hashing, you can now create a blockchain where each block is hashed and then is part of the input of the next block. And now blockchain that's only useful blockchain becomes more useful when you can distribute it. And we see here how you can share it in a peer-to-peer network. That's number 3. Number 4 is digital signatures. Now, the reason digital signatures comes in here is because, let's say Abe wants to say, hey, I'm sending $100 to Mike, right? So that's great. He'll send that information off to the peers that he's connected to, and it'll propagate throughout the network. But let's say Mike, what's to stop Mike from sending out a transaction and saying Abe sent money to Mike, right? Because there's nothing protecting, there's nothing validating who's sending out the messages, right? Anyone can send out any message, and that's where digital signatures, the fourth technology, the fourth and final technology to understand blockchain. So in traditional cryptography, in the more popular like AES and DES, so there's a single, when you want to encrypt a message, there's one key that you use to encrypt it, and then when you want to decrypt it, it's the same exact key that you use to decrypt it. So in public key cryptography, there's actually 2 keys. So there's one key that you use to encrypt. There's one key that you use to encrypt messages, and another key, a different. And if you try to use that key that you use to encrypt it, to decrypt it, it won't work. So you have to use the encryption key to encrypt messages, and there's another key, a second key that you use to decrypt messages. So now, if I have, and those two keys are called a private key and a public key. So now if I have my private key and my public key, and I tell everyone my public key, so now everyone knows my public key. Now if I take a message and I encrypt it with my private key, okay, the only way to decrypt that message is with my public key. So everyone can read it because everyone has my public key. But now but in addition to that, everyone knows that the message came from me because they were able to decrypt the message with my public key.
Public key lives on the blockchain, or is it distributed?
Nothing to do with blockchain yet.
I'm saying the public key. Oh.
Nothing to do with blockchain yet. This is a concept of where you have two separate keys. One key sends a message into encryption, and one key sends a message out of encryption. If a message comes out of encryption with a certain key, with a key that corresponds to a private key, then you know that private key was the one that encrypted the message. Okay, so there's a pair. There's a private key and a public key pair. If a message is decrypted with a public key, it can only have been encrypted with that private key. So if you know that this is my public key, and you can decrypt a message with this public key, then you know that I was the one that encrypted it. Okay, and this.
Your public key. Maybe someone else's public key.
So that's a whole nother meetup. But how to reliably tell people what your public key is. But on a very simple level, if let's say I want to send you a really long document, I can call you up on the telephone and tell you my public key. It'll be a couple, like 40 digits long. You can write that down, and then I'll encrypt my document with my private key. I'll send it to you, and then you can decrypt it with my public key. Right now, you'll have that whole long document, and you can be absolutely sure that I was the one who sent it, and no one else possibly could have sent it. Okay, so it works. It works like on the receiving end to know who sent it, but it also acts as a liability, because if there's a message that can be decrypted with my public key, it means that I encrypted it. So if I say that I owe Bob $1,000 and I encrypt it with my private key, and now that message can be decrypted with my public key, I can't say, oh, that wasn't me, because it could only have been me. Okay?
A private key is a hashing algorithm.
Let's keep them separate for now.
What's a private key?
So in digital signatures or in public key cryptography, a private key, there's two keys. There's a private key and a public key. They're pairs. They go together. So when I have a private key, there's a specific public key. Okay?
What
So
does the private key do?
it encrypts messages.
It's like an algorithm to encrypt that? What?
So there are algorithms, encryption algorithms like Caesar cipher or Atbash, right? So even the Caesar cipher, right, where you just flip around the alphabet. So that or you shift the alphabet. So that has a key. So let's say the key is 2, so you shift the alphabet by 2. So all ciphers have a key that you use to encrypt the cipher and decrypt the cipher with. Okay? So there's a private key. So there are public key algorithms that require public key algorithms for encryption require 2 keys, a private key and a public key. Okay? And you generate those 2 keys together. And the private key is the one you use to encrypt messages, and the public key that you generated together with the private key is the one that decrypts the messages. Okay, so if it goes in through the private key and it comes out through the public key. If it can come out with the public key, it means it was encrypted with the private key. Okay, and so now just an example here. So Alice is buying a car from Bob. She sends an email to Bob saying, "Dear Bob," so Bob says, "Yo, you can take the car and just send me an IOU." So, "Dear Bob, thanks for selling your car to me. I owe you $5,000, Alice." Okay. Bob says, "Yeah, I don't really trust you. Like, I need something more than just in writing, saying that you owe me. I need a way for you to not be able to go back on this. I need proof that it's you that sent it." Alice goes and generates her key pairs. Right? It's an algorithm to generate 2 keys, a public key and a secret key. She announces, "Hey everybody, my public key is 1FRJX, whatever the public key is." Everybody knows her public key. There's no way for her to take that back. Everybody knows it's her public key, and she controls the private key to that key. Now she goes and she encrypts this message with her private key. Okay? And this is the output, the encrypted message that was encrypted with her private key. Now, if now anyone could go and take this encrypted message and decrypt it with the public key that she made public, and we'll come back to this original message. So now Alice, because Alice encrypted this message with her private key, there's no way for her so she's the only one who possibly could have generated this encrypted message. Therefore, there's no way for her to go back and say it wasn't me. Okay? Now Bob says, okay, now, great, I feel safe. There's no way for you to back out of this. I've got your message, I've got your signature on that message, and we know it was you. Okay? So just when you're signing a message, it's a message plus a private key, and that equals a signature. So this is a signature. And when you're confirming or decrypting a message, so you take the signature, take that, plus a public key, and that equals the message. And you actually see this often. So just before we sat down, I just quickly Googled around to try to find one, and I found one on Reddit. So there was an Ethereum wallet online called My Ether Wallet, and there was some sort of fight, and one of the founders broke off and created My Crypto Wallet or something like that, and she posted the message on Reddit with her signature. So that's that over there. So you see here, she made a whole statement here, right? She wrote this whole letter here, and then she signed it with her key over here. All right, and there's a website called Keybase where you can store your public key. So this way, everyone knows that the lady who says that she wrote this actually wrote it, because you would have to check to make sure that this whole message encrypted with her public key does actually come out to that.
Unless it was stolen, of course.
Yeah, unless it was, obviously, I mean, you've got to keep your keys private, but that's assumed as a given.
It's another one.
Yeah. Alrighty. Okay, so let's review. Those are the four concepts. So we got hashing, method of summarizing information. It comes out with a hash or a digest. We got blockchain, which is a list of linked records. We have a decentralized network, which are basically copies of those blockchains. So what was the problem with a decentralized network? We said that anyone could send any message. Like Abe can send a message that Bob owes him $100, and that'll go into the blockchain. So what we have is digital signatures. So everyone who would join this decentralized network would publicize their public keys, and that way any message saying that Bob owes Abe $100 has to be signed by Bob. If it's not signed by Bob, we'll just discard it. Okay, and this right here really is, you can think of it as almost like a cryptocurrency. This would work. You have a decentralized network. People sign transactions, and it gets shared. So now the thing is, none of this is new. Okay, digital signatures have been around since the late 70s. Hashing has been around since even earlier than that. Blockchain was first discussed in the early 90s. Okay, so we got hashing, blockchain, peer-to-peer networks, digital signatures. All that stuff has been around, right? And we just conceptually created a cryptocurrency with the technologies that we have. In addition, the concept of digital currency has been around for a while. So there's something called eCash, there's something called B-money. So what did Bitcoin introduce, and why wasn't it something until Bitcoin came around? So the problem with all these solutions until now was that they all relied on a central authority, or so kind of like when you have like a BitTorrent. So all the pairs are connected and sending files to each other, but you still have a tracker. You still need somebody coordinating. So in a currency or in a token ecosystem, again, you need somebody who's in charge, somebody who's deciding what's true. So if somebody sends the same transaction twice, if somebody sends a fraudulent transaction, somebody needs to be able to decide, to be the final decider on what's true. And basically, the reason why it's not working is consensus, right? So you have this entire ecosystem, but there's going to be lots of fights, right? If you, like somebody said, what if somebody goes and changes the last block? What if two people send a new block at the same exact time? Right? Sometimes this is referred to as a Byzantine generals problem. And this really is essentially what the problem was until very recently, right? So all the technology for building a blockchain was around. It's just this one piece, this one problem of consensus that was holding everything back. Okay, so we need people to agree on transactions, and then also we have something called the double, for a malicious player, we have something called the double spend problem. Okay, so we have our blockchain over here. So now let's say Abe has some money, he sends it to Bob. So now we have this block right here. Now Abe goes and sends that same money to Charlie. Okay, so Bob is spending the same money twice. Right? Now some people have this block, some other peers have this block, and each of those peers are going to now start working on basically the chain forks. Everyone's going to be working on their own chain. So we need some way to decide which one of these is correct, and as quickly as possible get everybody back onto the main chain. So one way to do it is just to have it like a tracker, just to have a centralized authority. But having one person in charge is, first of all, we're relying on them. Second of all, if they get taken down, there was a company called Liberty Reserve that was actually pretty popular in the 90s, and they got shut down by the government. So again, if you have a central authority controlling everything, we have to trust them, and if they get shut down, then we're done for. So we need a way to decide which one to go to. Voting won't work because somebody could just spin a million botnets and just put in billions and billions of votes. So that's not going to work. So this is really the punchline, and this was Satoshi Nakamoto's brilliance: how to come to consensus on a blockchain. And his idea was consensus by proof of work. Okay. And in order to understand proof of work, first I'm going to go into a little bit more detail about how Bitcoin works, and then I'll get back to this. But like we saw, all the technology existed, and it was just consensus that was holding everything back.
So it's just consensus about the double spend. Is there anything else that would people?
Well, whenever
I send something, then I sent it. Right?
Forking. I mean, if
Double spend.
right, either maliciously or accidentally. Yeah.
Well, that's basically the only real issue. If not for this, then we wouldn't need consensus, because if I said I paid this guy,
Well, if you need consensus, you wouldn't need this altogether, right? You just.
Right. Okay.
Yeah. Okay, so a Bitcoin transaction. How does a Bitcoin? So in order to understand consensus by proof of work, let's just delve a little bit into how Bitcoin works, and we'll go back to that. So how does a Bitcoin transaction work? So I have, let's say previously we're middle of the blockchain ecosystem. Previously somebody had sent, so I have, here. Okay, so this is a Bitcoin wallet. So I'm going to bitaddress.org. It's telling me to move around my mouse to get some.
Generate random.
Thank you. What's the word? Entropy. Thank you. All right. And just to show you what Bitcoin wallet looks like. There we go. Okay. This is a Bitcoin wallet. Bitcoin wallet is my public key. It says share. That's my public key. That's my private key. This is a Bitcoin wallet. Okay. So in a Bitcoin transaction, somebody previously has sent me money to my Bitcoin wallet. Okay, and there's a transaction that says that somebody sent some Bitcoin to my wallet. Now, if I want to send that Bitcoin to someone else, what I have to do is I have to and when they sent me that Bitcoin, they said that this. What does it mean they send it to my wallet? Well, we saw a wallet is just a public key and a private key. So when somebody sends Bitcoin to a wallet, what they're basically they're putting some data into a block, into a transaction, and saying that whoever controls this wallet now controls this amount in Bitcoin that I'm sending to them. Okay? So there's a transaction out there in the Bitcoin ecosystem saying that whoever has the private key to this public key controls 2.5 Bitcoin. So now, when I want to send that Bitcoin to someone else, I can go back to that transaction, I can sign that transaction with my private key, right? Now everyone can look at the output of that signed signed transaction and know that, and they can see that whoever had the public key that was given rights to this Bitcoin signed this Bitcoin away to someone else. Okay, so I take my wallet, I take that transaction, I sign that transaction, right? And this is the input of 2.5 Bitcoin, and now I output that Bitcoin to some number of other wallets. So basically, I'm saying that 2.4 of that 2.5 Bitcoin should go to this wallet, and 0.0998 Bitcoin should go to this wallet. And again, what I'm saying is, this is a public key. So I'm saying whoever has the private key corresponding with this public key now controls 2.4 Bitcoin. Whoever has the private key corresponding with this public key now controls this Bitcoin over here.
How you know who sent it?
It's irrelevant. As long as the person who sent it has a private key corresponding with the previous transaction, we're good.
What does that mean to sign it? What was the signature?
Again, that's also very detailed. We're not going to get into exactly. It's actually a script. We're not going to get into that right now.
The person who sends the money signs it?
The person who sends the money says in this example. So this happened previously. Someone a year ago said, "There's these 2.5 Bitcoin that I have control over." Now there's someone else who has a public key, 16FLV, whatever. Whoever has a private key corresponding to that public key now controls that 2.5 Bitcoin. That's a transaction. That transaction happened before. So now I happen to be the person who has the private key corresponding to this public key. So this is my public key. Everyone knows it's my public key. That guy sent it to me a year ago. Now I have that private key. So what I can do is I can go back to that previous transaction, and I can sign. I take that previous transaction. I sign it. So now everyone knows that it was definitely me who signed that transaction. And I can now go and say in that transaction, I can say that 2.5 Bitcoin that everyone knows I have permission to because I have the private key for it, send it to these two other public keys.
So you can only claim Bitcoin when you're going to make an outbound transaction? Because I see here an input.
Yeah. Yes. Yeah. 1 second. All right. Good. Okay. So we have the total input. So we have a previous transaction that's giving me 2.5 Bitcoin. So that's the total input is 2.5 Bitcoin. So 2.5 Bitcoin. The total output is 2.49. It's 2.4.0998. It's 2.4998 Bitcoin. And then there's fees, and we'll get to fees later for 0.002 Bitcoin. So in total, that's equals to 2.5 Bitcoin. And now we take this transaction, we hash it, and this is now the hash of the new of this transaction. Okay. Now, right. So now I sent 2.4 Bitcoin to 1FRJ to a public, whoever has a public key, 1FRJX. A couple months later, that fella who had 1FRJX can go. So he has this transaction over here, right? And he can go, and there's 2.5 Bitcoin here. He can combine that with a bunch of other transactions that he got from other people. And again, this is all the input transactions to this single Bitcoin transaction has these input transactions, and it has these output transactions. And again, to 1FRJX. So he's sending it to whoever has the private key for 17HN, sending 0.199, and 1FRJX is his wallet. He's basically just sending back 11 Bitcoin to his own wallet. And the reason why he has to do that is because you can't this single transaction that has 2.4 Bitcoin, you can't send a piece of it. So when you sign this transaction, you're spending this transaction. So when somebody first sends you a transaction, it's an unspent transaction, and then when you want to spend it, it becomes a spent transaction. So you must use all of the Bitcoin that is in that transaction. So if somebody sent me 2.4 Bitcoin in one transaction, I must send all that Bitcoin. And I can't. So let's say I only have to send someone 1 Bitcoin. So what I do is I send them 1 Bitcoin, and I send 1.4 Bitcoin back to myself. So now I'm creating two new unspent transactions. One transaction is going to that new person. That's this one over here. The numbers don't make sense here. So don't look at that. But one transaction is going to that new person, and one transaction is coming back to myself. That's myself, and that's a new person. So now there's this unspent transaction. Someone else now controls, whoever has a private key for this. And this one is going back to me, and again, it's creating a new transaction that I can sign over to someone else.
Two things. First of all, this all seems very tedious when you start racking up the transactions you didn't spend. You have to start doing math
Yeah.
to figure out which transactions will help you along the way to your outbound transaction.
Yeah, your wallet takes care of that.
Your wallet takes care of that.
Yeah.
Okay. And what do you do? Where does the Bitcoin that you transacted to your own wallet go? Since you don't no longer have to sign that, or do you?
No, it creates a new transaction.
Oh,
There's a new unspent transaction in your wallet. Yeah. Because you sign the previous transaction. It's like we saw before, right? I have this message and I sign the message. So now I created this message so everybody knows that whoever had the public key wrote this message. Whoever had the private key for this public key wrote the message. So the same thing with the Bitcoin transactions. I signed the previous transaction with my private key, and now everyone has this signed transaction, and they can verify verify it with the public key that everyone knows owned that transaction. Okay. Okay. So that's Bitcoin transactions, and just some tidbits. The Bitcoins can go there. You can use up to 8 decimals. So that's 1/1000th of a Bitcoin. And like you said, really it's a misuse of terminology. You don't own Bitcoin. You have control of unspent transactions. There are unspent transactions that you can sign over to other people. Yeah. Okay. So now I create a Bitcoin transaction and I send it out through the peer-to-peer network into the Bitcoin ecosystem. And that's where Bitcoin mining comes in. So somebody creates a transaction, they send it out to the whole peer-to-peer network, and eventually it gets to a miner. Now, what does a miner do? So they do a few things. One is they verify the transaction is unspent, right? Make sure that this transaction that you're signing over wasn't used before, and that it's actually signed correctly. That whoever signed for this transaction was the one who had the public, who is the one who had the rights to it. Because when the input transaction was created, whoever sent it to me, when they signed the transaction, part of what they said was whoever owns my public key, that person's public key, is the new owner of it. So now I'm the new owner of it. The signature sign. So there's a message that says Bitcoin wallet A is sending Bitcoin to Bitcoin wallet B. Right, and Bitcoin and Bitcoin wallet A there signs that transaction. So now let's say I'm Bitcoin wallet B. So now when I sign that transaction, so that transaction said that B controls it.
But in your example, there's this public key database where people can go check what your public key is.
No.
How do we do that here?
No. So that was just a concept of digital signatures. Applying it here. So there's no database of public keys. When a transaction is created, the transaction defines the public key of the recipient wallet in the transaction itself. So we say the recipient wallet is ABC, and they sign that, so we know it's verified. Now, when that recipient wallet, let's say I received it, so I have this transaction. So if I want to spend this transaction, I sign it with my private key of that recipient wallet that I own.
You're essentially giving the message and the key in the same message.
Yeah.
What's the difference?
Yes. I'm sorry. Yeah. In the transaction is the public key of whoever's receiving it.
The public key is the wallet.
Yeah.
You can think of it, the public key is the wallet.
It is.
I say
It is the wallet.
Okay, so
Yeah. Yeah.
You have to make sure that you're sending it to the right public key.
Yeah. It's very hard to make a mistake
And how are you verifying it?
because whoever you're sending it to is going to send you that public key.
You have to.
It'd be a professional copy and paste.
Yeah. Professional copy and paster. Yeah.
Make sure no one's accepting it and switching it.
So you
Make
send
sure
it to
no one's
verify key.
accepting it and switching it.
Yeah. Yeah.
What essential authority, how do you stop one person from having the same public key? Because technically there can be
Where's that? There we go. Yeah, so I wrote this down. I skipped this before. But there are 2 to 256 possible Bitcoin keys. Okay, that's more than the number of atoms in the world. Okay, not all of those, because of the way the Bitcoin protocol, the scripts that the Bitcoin protocol uses, only 2 to the 160th keys are actually available. But just to give you an idea, so there's approximately, I Googled this, there's approximately 7.5 quintillion grains of sand on planet Earth. Okay, if each of those grains of sand was itself planet Earth and had all the beaches, right, it still wouldn't equal. Right, and take all that sand, it still wouldn't equal the number of possible keys that there are.
If you believe in evolution, then
Yeah. So there's lots and lots and lots of Bitcoin keys, and you can try, like, you can't brute force it. Like, it'll take you longer than the age of the universe, if you believe in evolution, to actually go through to brute force this and try all the different keys. Okay, so that's the first thing that the Bitcoin miner does. He verifies the transaction is unspent and that it's signed correctly by the wallet that received it. Okay, then they go and they gather several hundred unconfirmed transactions. So they're receiving a bunch of transactions. What they do is they take a bunch of transactions and they hash. So all those transactions, they take all those transactions and they hash them all together. Okay, so you end up with a single hash of all the transaction. And then they take a few pieces of information. They put together a few pieces of information. So one is a hash of the transactions. That's this. The hash of the previous block, the current time, and then they have to find a nonce. We'll get to that in a minute. From 1 to 2,147,000,000. So basically, they have to take all this information and then find a nonce between those two numbers. And then they have to find the number, the nonce, that will make the block result in a successful hash, right? And that's going to go back to what we did with Hashcash.
who verifies the current time?
Who verifies the current time?
Once they get the nonce, that's successful hash.
Yeah, so I mean, what's your question?
Why is that part of the mechanism?
The current time? Oh, I mean, part of the protocol says that you can't, I think something to the effect of you can't accept a block that's more than 10 minutes in the past.
Someone else verifies this block?
Yeah, so you're going to create this block, find the nonce that makes this block hash to the correct number, and then immediately send it out to everyone else. And then when all the other miners and all the other Bitcoin nodes get this block, they'll double check your work. Yeah, they definitely will, and they won't accept it if it doesn't work.
The miner creates the block?
Yeah, this is what a miner does. They take all the transactions, they hash them. So they take the hash of the transactions, all this information, they find the nonce, and that's the block.
That way people can't pre-compute. Who decides how many transactions that block is doing?
The miners, there's a limit, but that's a whole other subject. But there's a limit. But the miner can take. I've seen blocks with no transactions, 0, or just one Coinbase transaction, or 2,000 or 2,500 transactions.
How are they getting transactions that weren't sent to them?
It's a peer-to-peer network. So if you're connected to 3 or 4 or 5 Bitcoin nodes, and they're all connected 3 or 4 or 5,
Okay,
so within a few seconds, you any new transaction you'll get.
So
I'm guessing, how do you know it's unverified?
How do you know?
No.
Oh, I mean, because if you're a Bitcoin miner, you have a copy of the entire blockchain. You have all the previous blocks, so you know if this transaction is a new one, is a new one, or it's been put into a.
What I'm asking is that, let's say Joe sends Bitcoin to Frank, and then Mark is a miner.
Right.
So what is it talking? What do you mean?
So what does it mean that Joe sends Bitcoin to Frank?
Because he makes a block that sends.
He's not sending it to Frank. He's creating a new transaction, saying that this Bitcoin that belonged to my wallet is now going to go to that person's wallet, and then they put it out into the network.
Right.
That's what it means.
So he intercepts it.
Eventually, a miner will get it.
So how is this? My question really is, how is this legal? Meaning, because you're basically taking something that was supposed to go to Frank's wallet, and
It's
you're
not
kind of grabbing
accepting
it.
the wallet, he's confirming it, he's verifying it.
But
It's
again,
like putting it on a bulletin board and says like, hey, Joe is sending $10 to Alice, and everybody who walks by, you put it on the New York subway. Everybody walks by, writes it down, and look through the database, like, okay, Joe has that money, okay, very good. And then they go right down and say, yep, that's right,
Right.
one, they hash it, and it's all
A
verified.
bulletin board is a good way to think of it, and just think of it where everyone has their own bulletin board.
At the end of the day, the Bitcoin goes to Frank, not to you.
What does it mean? Again, you're not. So okay. So this is a Bitcoin block. So miner is mining a Bitcoin block. So just to reiterate what a Bitcoin block is. So a Bitcoin block is made up of the header and a body. In the header, it has a version number, has a previous hash, it has the hash of all the transactions that we saw before, the time and a nonce, and then in the body are all the transactions, which can be a few thousand or none, all the transactions that are included in this block. And again, this transactions hash is all these transactions hashed together in a very specific way. So
finding the nonce is what makes it take all the time. That's the whole.
yes, yeah,
It's only from 1 to 2 billion.
And that's
like a
proof
very
of
yeah. So that's gonna be the proof of work. So you take all this information and then you have to find a nonce that when you add this nonce, all this information gives you a hash that has a certain number of leading zeros.
2 billion is high enough for a computer to take that long. Sandwich.
4 billion. Yeah, it takes
Computers can't take like seconds for 2 billion numbers.
very, very powerful computers can probably do it in a few minutes.
Really?
Yeah.
For each number, you have to run the hash function.
Again, if I do this, right? Hello world, I want to find six leading zeros, right? Oh, so that just took a few seconds. Oh, so that one is just a lucky break. But here, so if I want to find a hash that starts with 7 zeros, so that's 16 to the 7th, that's 268 million, right? Not even in billions yet, 268 million. And right, it looks like it's going to take about an hour. There's a MacBook Air, so I mean, do the math. Okay, so this is a Bitcoin block. This is what the miner is doing. They're taking a bunch of transactions, verifying, making sure they're unspent, making sure that they're signed correctly, hashing them all together, and then building this block. As soon as they get this block, they're immediately going to send it out to the Bitcoin ecosystem saying, hey, I found the block, and let's start working on the next block.
How do they verify it wasn't spent?
What's that?
How do they verify it wasn't spent? How do they know they didn't?
Well, all the Bitcoin miners all have to have a copy of the entire blockchain going all the way back.
Yeah, but how do they know that their latest block is the last block?
Because they're connected to the network.
They have to have the last block.
They're assuming that they have the last block.
They
Yeah.
don't have to. I mean, they're just verifying a piece of it.
No, because you're
They need
adding this
previous-
block to the previous you must have the previous block to begin with because you need the previous hash.
block of the verification.
The previous this block over here. You have to have this block because you need that hash.
Transactions. They don't need all the transactions.
Well, you need all the transactions in order to know which transactions to add into your new block.
But subsequent transactions they don't need for this.
What do you mean?
More transactions happen while they're doing.
Oh yeah, no, it doesn't matter. So at any given time, there could be 10,000 outstanding transactions. Okay, and let's say there's 100,000 Bitcoin miners out there trying to mine Bitcoin, right? They'll all probably be working on somewhere between 1,000 and 2,000 transactions. All of them working on different transactions. So because there's 10,000 outstanding transactions, you just pick the ones that you want and work on those and publish them. Then as soon as your block is accepted by everyone else, they drop those transactions that were included in your latest block and start working on whatever else is in a pool.
Which block is accepted? Two miners create a block simultaneously.
Okay, so we'll get to that in one sec. So just one cool thing to notice over here is we have this transaction right here. You see here that there's no input over here. There's no input, there's only an output transaction. And this is called the Coinbase, and that's where company Coinbase got their name from. And basically the way this works is that every time a miner, so it takes a lot of effort to find this nonce. Every time a miner finds this nonce and publishes a block, as part of the protocol, they can give themselves Bitcoin out of thin air. They create their own Bitcoin and add it to their own wallet. And this is the reward for putting in the effort to mine. So it started off in 2009. It started off at 50 Bitcoin, and the way the protocol works is every 210,000 blocks it halves. So in sometime in 2013, it went down to 25 Bitcoin reward, and then about a year or two ago, it went down to 12.5 Bitcoin. Okay.
Why would they continue mining?
Because Bitcoin is deflation. Bitcoin is worth a lot more now than it was 4 years ago.
They're assuming that it's going to be inflation. Otherwise, people are just going to stop mining.
Yeah, I mean, they're assuming that this is going to be worth something. That's why.
Once people stop mining, then this whole thing collapses.
No, they also get fees.
Kind of. So well, as soon as people stop. So another thing. Hold on one second. So another thing. So the reward adjusts every 4 years, every 210,000 blocks. How do you figure 4 years, 210,000 blocks? That's because the Bitcoin protocol is configured to adjust the difficulty. Right. This is the hash that you're trying to find has to be lower than a specific target. How do we decide what that target should be? So the target is called the difficulty, and we adjust the difficulty so that on average a new block is created every 10 minutes. Okay, so if a lot of new miners join the ecosystem and now new blocks are being generated every 7 minutes because of the difficulty isn't hard enough and there's more miners and they're finding it faster. So the protocol every 2 weeks readjusts itself and says okay, on average in the last 2 weeks blocks were found every 7 minutes. Let's make this slightly more difficult. Let's make them find one more zero there. And now it'll take a bit more than 12 minutes, right? If a bunch of miners start dropping off, and now blocks are taking 20 minutes to create, so again, every 2 weeks the protocol will readjust itself and say, okay, miners are dropping off. It's too difficult. Let's reduce it. Basically each node looks at it. So when I create a block, I send it out. All the other nodes have to accept it, right? So all the other nodes readjust the difficulty themselves, and they'll only accept blocks that meet the criteria.
Are the transactions themselves stored on the blockchain?
Yes, yeah, the transactions themselves are stored on the blockchain.
Do the transactions count for these block counts?
No. So you can have thousands of transactions in a single block.
I mean, they only
Yeah.
live inside of the block.
Okay, so this is the last slide. Okay, so and so after we understand all that, so this is where proof of work comes in. So what Satoshi Nakamoto said, hey, one second, we have all this technology that we can use a block to create a blockchain. The problem is consensus. We have this hash cache thing that finding the nonce to create a block, right? So finding a nonce is not a long complex math problem. It just takes work. It's just trial and error, right? The point is there's no way to. The more computing power you dedicate, the more likely you are to find the next block. There's no shortcuts. That's the point. There's no way to fool this system. Either you're doing the work or you're not doing the work. With votes, you can create botnets, but with just doing the work, you're doing the work. So by this nature, blocks will be mined faster. Okay. So basically, what his Einfall was that you don't have to assert consensus. Consensus could be emergent. Okay? If we have two kids in the class and I ask you, and during recess I say which one is more popular, right? I don't have to determine which one is more popular. The one with the most kids around them is the most popular, and so as an equivalent of having the most kids around you is having the most work around you. And what Satoshi Nakamoto realized is that the longest chain is the one with the most participants. So let's say I have this blockchain, right, and I have block 3 here. Somebody spent some money, a transaction in block 3, and they're a malicious actor. They want to double spend. They want to spend it again. Okay, so they're going to start working on a new block that's a child of this block, not a child of this block. But in the meantime, everyone else in the ecosystem is going to be working on this block, right? And so since there's no shortcuts, and by nature the blocks will be mined faster by a group. Just the more people you have mining, the faster you'll build blocks. This block will automatically will almost for sure be generated before this one individual spends that block. So now if this person spends this block, actually creates this block finally, and he publishes it to the Bitcoin ecosystem. So everyone now sees, okay, so we have this one parent block. We have 2 blocks tacked on over here and 1 block tacked on over here. This is the more popular block. I'm gonna continue mining on this block. Whoever mines on this block, like no one's on this block. This block has no value, and that's why everyone. So basically it just emerged. So what gives Bitcoin value? What gives Bitcoin value is the fact that everyone is on it. How do you determine if everyone's on it? Well, if it's the longest chain, it means everyone is on it, and that was what Satoshi Nakamoto introduced.
You could have someone with a lot of computers.
What's that?
You have someone with thousands of computers who will have a lot of transactions.
Yeah, I mean, but again, it's just computing power. You can actually spend that. You can use that computing power. But if you have billions of dollars invested in the Bitcoin ecosystem, you're not going to want to start messing around with it. Like this isn't going to give you anything.
Because one person technically theoretically has over 50% of the computing power.
They can change. Yeah.
And is this how forking works?
So this.
You just get more people to start
So
mining
again,
it.
the way forking works is if the protocol. So we're officially done.